Welcome back, everyone. As I promised, today we're going to talk about bijections. So what makes a function a bijection? What makes a function a bijection is for it to be both one-to-one and onto. Now, I just want to note in terms of parts of speech, one-to-one and onto are adjectives, but bijection is a noun. So a bijection is, if you want the adjective form, a bijective function. So if you look, this is just a portmanteau of bijective and function. Now, strictly speaking, you now know everything there is to know about a bijection because you understand what it means to be one-to-one and what it means to be onto. But it turns out that rather interesting things happen when you have a function that is both. And so I think this actually makes the most sense if you think back to these dot diagrams, where you're indicating the map with arrows and so on. And so, if you think back to what onto means and what one-to-one means, you can describe both of these in terms of arrowheads. And so, what does one-to-one mean? It means at most one arrowhead per dot in the codomain. No two arrows map to the same place, so that's saying no two arrowheads point at the same dot, and so that's saying really there's less than or equal to one arrowhead per dot. On the other hand, if I look at what onto means that every dot has an arrowhead pointed to it, so onto really means that there's greater than or equal to one arrowhead per dot. And so if you look at this greater than or equal to 1 and less than or equal to 1, then you get a really good sense really quickly of what exactly it is that being a bijection means. Namely, if a number has to be greater than or equal to 1 and less than or equal to 1, it has to in fact be exactly equal to 1. And so, in fact, what does being a bijection mean? One way to frame it is that being a bijection means that there's exactly one arrowhead per dot. And so if you look over here, that actually means there was no way I was ever going to be able to make this into an example of a bijection. Why not? Because there were 4 dots over here, which was going to mean I was going to have 4 arrows, and hence 4 arrowheads. But there were only 3 dots over here, and so I was going to actually have to use 4 arrowheads, which was not going to be able to be one arrowhead per dot. So in fact, in order to possibly make this a bijection, I would have to throw a 4th dot over here and draw something like this. Now, a consequence of this is that if A and B are finite sets, and I have a bijection from A to B, and what does that tell me? Well, that tells me that the size of B, that is, the number of dots in the codomain, is equal to the number of arrows. But the number of arrows, well, this is just the definition of function. The number of arrows is equal to the number of elements in A. And so what this says is, in fact, if there's a bijection from A to B and A and B are finite sets, then A and B have the same size. They have the same number of elements. They have the same cardinality. And this is part of what I alluded to at the end of the last video, which is what I'm going to call the Pigeonhole Principle Part 3. So, like we've done before, I want to go through and give you a list of functions, and for each of them I want to ask, hey, is this function a bijection or not? Now, just like before, I want to write down what it means for a function to not be a bijection. So, namely, I want to write down what is the negation of is both one-to-one and onto. Well, it is not one-to-one or is not onto. So what do we have to do to show that a function is a bijection? We have to prove it's one-to-one in exactly the way that we've shown functions are one-to-one in the past. And we have to prove that it's onto in exactly the way that we've shown that functions are onto in the past. What do we have to do to show a function is not a bijection? Well, we have to choose to show that it is not one-to-one or not onto. Here is where you really have to make sure you do your scratch work first, because imagine the following nightmare scenario. You're trying to decide if a function is a bijection, and you go through a great deal of labor to prove that it is one-to-one, and you type all of that up. And then you start typing up a proof that it's onto, but you discover that your proof that it's onto is wrong. It's actually not onto. And so you write up that. In this nightmare scenario, you've actually written up an entire part of a proof that is completely unnecessary. Because once it is not onto, whether it's one-to-one or not is irrelevant to whether the function is actually a bijection or not. So act carefully when you're thinking about whether functions are bijections. Okay, so let's look at some examples. Is this function a bijection? And so when you look at this, you probably toy with it and think, okay, well, there's a squared here. And maybe the squared here makes you think, oh, it's not going to be a bijection. But then you see the pluses here, and then maybe the pluses again make you think that this is going to be a bijection. And so if you look at this closely, what's actually true, and you might be able to convince yourself of this sort of intuitively, is that this function is one-to-one, but it's not onto. So which of these things do I have to prove in order to prove that this thing is not a bijection? And that's right, I have to show that this thing is not onto. The fact that it is one-to-one, I could prove, but it doesn't show anything that's relevant to the question. So remember, to show that something is not onto, we're going to grab an element of the codomain. In this case, I will boringly choose 1. And then I will note that for all a in the domain, f of a, which is just a squared plus 1, well, the smallest a could be as 1. So the smallest a squared can be as 1. So this number is in fact always at least as big as 2. And so in particular, f of a is not b. And so what does that tell me? B's not in the image of f, and so f is not onto. And as soon as f is not onto, it's not a bijection. How about this function? We're taking r to r, and we're mapping x to the natural log of the absolute value of x plus 1. Now, there's a lot to be distracted by here. But if you look at this closely, I think there's one piece of what's written here that tells you what the answer is going to be. And I really think if you don't see it yet, you should pause the video and look at it for a minute before you continue. What's the piece here that tells me the answer? And the piece here that tells me the answer that I want to draw your attention to is this absolute value of x. So what is the absolute value of x here telling me? It's telling me that this function can't possibly be one-to-one. No matter what complicated, messy thing this function happens to be, it's not going to be one-to-one. And how do I know that? I know that because if I put in a positive value for x, and I put in the negative value for x, I'm in fact going to get back exactly the same answer. So remember that to show something is not one-to-one, I just have to give you two different values in the domain that map to the same element in the codomain. Really, two arrows that point at the same dot. And so in this case, the arrow originating at 2 lands at the dot natural log of 3, and the arrow originating at -2 lands at the dot natural log of 3. And so these two things are equal, even though 2 and -2 aren't equal, and so g is not one-to-one, so g is not a bijection. How about this function? So again, take a moment, make sure you understand what this function's doing. What is it inputting? What is it outputting? And how is it turning the input into the output? So what's happening here is I'm starting with a subset of the numbers 1 through 5. It could be all of them, or none of them, or anything in between. And then what I'm doing is I'm taking 5 out. What if 5 is already not in the set? Well, great. I just keep it out. And so then I get back a set, but now, instead of being a subset of the set 1 through 5, well, I now know 5's definitely not in it, because I took it out regardless. And so I'm left with a subset of the numbers 1 through 4, which again could be everything or nothing or anything in between. So is this function a bijection? And so really I'm asking here, is it 1-to-1? Is it 1-to? In this instance, as it happens, this function is not 1-to-1. Can you give me two things that map to the same place? So if I take h of 1, 2, 3, 4, 5, what am I going to get? 1, 2, 3, 4. Is there anything else I can take h of to get 1, 2, 3, 4? Well, why yes, there is. I can also take h of 1, 2, 3, 4. And if I do that, well, again, I'm taking 5 out, but 5's already not in it, so I also get 1, 2, 3, 4. And so just this fact alone, that these two inputs give me the same output, is enough to tell me that this function is not 1-to-1. Now there's an alternative proof that you might see here, and that alternative proof is to use the pigeonhole principle. Namely, if I look at our theorems, I know that the size of the power set of 1, 2, 3 up to 5 is 32, right? Remember, the size of the power set of a finite set is 2 to the power of the size of the set. But on the other hand, the size of the power set of the numbers 1 up to 4 is 2 to the 4th, that's only 16. But remember what our third part of the pigeonhole principle said. It said that there exists a bijection between two sets if and only if those two sets have the same cardinality, again, as long as those sets are finite. So in fact, by the pigeonhole principle part 3, not only is this not a bijection, there doesn't even exist a bijection from this power set to this power set. And so if there doesn't exist a bijection between these two sets, certainly this proposed function is not a bijection between these two sets. Even better, if you wanted to be more explicit, you could think all the way back to the first pigeonhole principle, which told you that if there were more elements in the first set than the second set, that is, more elements in the domain than the codomain, then the function couldn't possibly be 1-to-1. And so you would know the thing you should be looking for is a proof that the function's not 1-to-1, which is in fact what we found. Here's yet another function. We want to know, hey, is this function a bijection? So here, I think we probably don't have enough intuition to really guess the answer, but we also probably don't have enough intuition to start just guessing elements that might map to the same place, or guessing elements that might not be in the image. And so when we lack alternatives, I think our best option here is actually instead to just try and prove it, and if it's true, hopefully great, we'll prove it, and if it's false, hopefully we'll see why. So any proof that something is a bijection is going to break into two sections. I don't know if this is going to be a proof yet, but I'm going to start by labeling the section 1-to-1. And so what do I need to show that a function's 1-to-1? Remember, I need to show that if f of one thing is equal to f of another thing, then those two things are actually equal. Now, normally I would say if f of x is equal to f of y, then x is equal to y. But that is likely to cause some consternation if you look at this and see that I've already used x and y, and so that's not really a wise choice. So I really want to here give better names to my inputs. So I'm going to suppose f of a comma b is equal to f of c comma d. Again, I'm supposing two inputs give the same output, and my goal, if I'm trying to prove it's 1-to-1, is to show that in fact those two inputs are the same. That is, I'm trying to show that a is equal to c and b is equal to d. So what have I supposed when I've supposed that f of a, b is equal to f of c, d? Well, I've supposed that 2a minus b, comma a minus 2b, is the same thing as 2c minus d, comma c minus 2d. And so, again, that's really giving me a system of equations. 2a minus b is equal to 2c minus d, and a minus 2b is equal to c minus 2d. Now, reminder, when you have a system of equations, there are a couple different ways you can proceed. One is to solve and substitute, and the other is to sort of combine the equations to try and eliminate variables. In this case, I recommend the second one. Try and combine these equations to eliminate variables. Namely, I notice if I multiply the top equation by 2, that is also going to involve a 2b, and also a 2d for that matter. And then I'm going to be able to cancel that 2b and that 2d with this 2b and this 2d. So I am rewriting this system of equations as 4a minus 2b is equal to 4c minus 2d, and I'm leaving the second one the same. And now what I actually want to do is subtract the second equation from the first equation. So if this is equation 1 and this is equation 2, then equation 1 minus 2 gives us, okay, so 4a minus a would be 3a, minus 2b minus 2b will give me 0. 4c minus c will give me 3c, and then minus 2d minus 2d will give me 0. So equation 1 minus equation 2 gives me 3a is equal to 3c, and so that gives me a is equal to c. Now, if you remember what it is I'm trying to do, I'm trying to show that since these two inputs gave me the same output, the two inputs are the same, that actually gets me halfway there, because this has shown me the first part, a and c, are actually equal. I still need to handle b and d. How am I going to handle that? Well, I'm going to use this equation and substituting that into, and I'm just going to put it back into, say, equation 2. So I just replaced the a with the c, so that c minus 2b is equal to c minus 2d. So the c's cancel, and I'm left with minus 2b equals minus 2d. And so what does that end up telling me? That ends up telling me that, in fact, b is equal to d. And thus, what have we shown? We've shown that a comma b is equal to c comma d. So our function is 1-to-1. Now, are we done yet? Well, no. We learned the function is 1-to-1. So either it's also onto, in which case we need to produce a proof of that, and then the function's a bijection, or it's not onto, in which case that was a large waste of time. But we're not going to know until we try. So let's try and show that this function f is onto. So I'm going to start with an arbitrary element of the codomain of f, and I'm going to call it a comma b. Now, what is it I want to show? I want to show that there exists an x comma y in the domain that maps to a comma b. Well, to figure out how to do that, I'm going to need to do scratch work. Namely, I'm going to want to figure out when is f of x comma y equal to a comma b. That is to say, when is 2x minus y comma x minus 2y equal to a comma b. Or, in other words, I'm trying to solve the system of equations 2x minus y equals a, and x minus 2y equals b. So, 1 lets me solve for y, so that will give me y is equal to 2x minus a, which I can then substitute into 2, and that will give me x minus 2 times 2x minus a is equal to b. So that will give me x minus 4x plus 2a equals b, which is to say minus 3x is equal to b minus 2a. So x is minus b minus 2a over 3, Or, if I want to write that more cleanly, that is 2a minus b over 3. Remember, this page is scratch work, so I don't have to write it up super neatly, just neatly enough that I know what my x is supposed to be in my proof. And then what's y? Well, y is 2 times x, so it is 2 times that, minus a. I'm just copying out of that equation. So this is 4a minus 2b over 3 minus a. A is 3a over 3, so this is a minus 2b over 3. So that's supposed to be my y. I say this a lot lately, but I just want to remind you, in this scratch work, what we've actually proved is the exact opposite of the thing we want to prove. Namely, what we've actually proven here is if there's a solution to this equation, this is the solution. But what we actually need to prove that this is onto is this is a solution. And so again, there's a big difference between if there's a solution, it's this, and this is a solution. So I now need to actually do that second piece. So I need to hop back to my proof here. And I need to prove that this x comma y actually is a solution. So I'm going to do that. Let x comma y equal, and so this is 2a minus b over 3, comma a minus 2b over 3. And now really all I have to show is that if I take f of this, I get a comma b. So f of x, y, if I just apply it straightforwardly, is going to be what? It is going to be 2 times 2a minus b over 3 minus a minus 2b over 3, comma, and then y will be 2a minus b over 3 minus, and then 2 times a minus 2b over 3. All I did here was use my formula that defined f. Okay, the very beginning, f was this. It took x comma y to 2x minus y comma x minus 2y. And so I went ahead and plugged in that value for x, that value for y up here, which gave me this. Okay, now I sure hope this simplifies a good bit, because we know what it's supposed to simplify to. Okay, so in the first slot, everything's over 3, so that's good. So my numerator is going to be 4a minus 2b, and then minus a minus minus 2b, so plus 2b, comma, and then everything here in the second term is also over 3, so it'll be 2a minus b minus 2a minus minus 4b, so that is plus 4b. Okay, and so maybe now we're to the point where you can see where this is going in your head, because now these 2b's cancel, these 2a's cancel, and so this is now 3a over 3, comma 3b over 3. And just like we hoped, that is a comma b. And so I have now completed my proof that this function is onto. Namely, I have started with an arbitrary element in the codomain, and I have shown that I can write down an element that maps to it. So f is onto. And thus putting those together, since f is one-to-one and onto, f is a bijection. So therefore, we can go back to the very start of this proof, and we can say, yes, this thing's a bijection. Here's the proof it's one-to-one. And we wrote down that. Here's the proof it's onto, and then we wrote down that. And remember, there was this whole sheet of scratch work in the middle that does not need to be typed up or be part of our solution in any way. This is something you have to do unless you're just going to guess 2a minus b over 3 and a minus 2b over 3 out of nowhere. which, I mean, you're welcome to do. But barring some sort of psychic intuition that that's the thing you're looking for, you're going to have to do this scratch work, but it's not going to be something you need to turn in. Okay, so here's the pigeonhole principle part 4. Suppose that A and B are finite sets. They both have the same cardinality, and I have a function f from A to B. Then TFAE, which stands for the following are equivalent. And you're going to see this phrase a lot written by various math faculty. In fact, if you've already had linear algebra before this course, you've probably seen this written on the board 100 times. Okay, so here are 3 different statements. And we know what each of these statements means. One of them is that f is 1 to 1, one of them is that f is onto, and one of them is that f is a bijection. And when I say the following are equivalent, what I'm saying is every pair of these statements is logically equivalent. So that is to say, if I write down each of these things as a bubble, there's a biconditional between every pair of them. So 1 if and only if 2, if and only if 3, if and only if 1. And so when I make this the following are equivalent statement, what I'm really doing is I'm really telling you 6 different implications. And so when someone gives you a TFAE theorem, they're giving you a whole bunch of implications, and you can use any one of those implications anytime you want. Now, I'll go ahead and note, how would you actually prove a TFAE statement? You probably will not have to do this as an undergraduate, but what does a proof look like? The proof of a TFAE statement, generally what you do is you find the right order to write down all of the statements, and then you prove the implications around in a circle. So in this case, you could prove 1 implies 2 implies 3 implies 1, and even though this is making 6 implications, you actually only need to prove 3 implications. And why is that? That's because if I prove 1 implies 2 and 2 implies 3, well, if I just put those 2 together, that tells me 1 implies 3. So I don't also have to prove that. And so in linear algebra, you'll see this thing that's got like 20 different pieces about the following are equivalent, the matrix is invertible, the determinant is 0, the kernel is trivial, etc. And so in order to prove that, if there's 20 statements, you need to prove 20 implications, but then you get 190 implications out of it that you could use however you like in the future. It's a good deal, but it's a mess. So now let's zoom in, now that we've talked about what the following are equivalent means, let's zoom into what this actually says, because what this says is a little strange. So we've got 3 things, and it's telling me all 3 of them are the same. Now, what's especially jarring about the claim that all 3 of these are the same is that the third statement here is literally the same as saying the first 2, right? 1 to 1 and onto is just the definition of a bijection. So this at first seems like a paradox. It seems like, oh, as soon as I know the function's 1 to 1, somehow I get the rest of this stuff for free. That's exactly what this is saying. If I have 2 finite sets that are the same size, note that hypothesis is really important, then as soon as I know that the function is 1 to 1, I know it's onto. And hence, if it's 1 to 1 and onto, it's also a bijection. And as soon as I know it's onto, I also know it's 1 to 1. So these 2 very different looking conditions suddenly become the same condition under the hypothesis that you have a function between finite sets of the same size. Now, I can make this statement a little bit more intuitive if I think of a function that is more concrete. So let's say I have 12 people sit on 12 couches. This gives me a function from the set of people to the set of couches. And here a person, I'll call them person X, they get mapped to the couch person X sits on. And now the fact that this is a function is just the statement that every person is sitting on a couch. Now, I've made no assumptions about how the people are sitting on the 12 couches. So, for example, it might be that all 12 people sit on one really big couch and leave the other 11 couches empty. I'm not ruling that out. That's distinctly possible. It would still be a function. There would be no problem. But in terms of people and couches, what do one-to-one and onto mean? And so let's write that down. So what would it mean for this function to be one-to-one? Well, it would mean no two different inputs go to the same output. So in this instance, the condition one-to-one is exactly the condition no two people sit on the same couch. What's the condition onto? Well, the condition onto here is the statement that every couch has at least one person sitting on it. So what is this theorem, the Pigeonhole Principle Part 4, what is it saying? Well, it is the observation that in the instance that we have 12 people and 12 couches, that if someone is sitting on every couch, then no two people can be on the same couch. Because if two people are on the same couch, then really they could occupy at most 11 couches. Likewise, if I know no two people are sitting on the same couch, then it has to be that someone's sitting on every couch. Because if only one person's on each couch and there's 12 people, they have to take up 12 couches. And so in this very specific instance, knowing that the function is onto, or knowing that it's one-to-one, actually convey exactly the same information. During quarantine, I've been entertaining myself by doing Sudoku, because there's not a whole lot else to do. And so in Sudoku, you have this 9x9 grid. And there's all these different requirements about the 9x9 grid. But in particular, they say things like, each digit 1 through 9 occurs in each row, meaning occurs at least once. But also, each digit 1 through 9 occurs in each row at most once. And so each of these leads to a different kind of logic. So for example, if I happen to show that there's a 3 here in the upper left corner, then the second piece of reasoning here tells me that none of the digits over here are 3s. Whereas, if I show, for example, there can't be a 6 anywhere in this spot, and there can't be a 6 anywhere in this spot, and in fact, there can't be a 6 anywhere in this spot, so the only place a 6 could go is over here, the first requirement then tells me, okay, well, if this is the only place a 6 can go, there has to be a 6 here. And these are two very different logical statements. The statement that, hey, there's at least 1 3 in this list of numbers, and there's at most 1 3 in this list of numbers. But the key thing here is that what's really going on is we have a function from the 9 boxes in the row to the digit each of those boxes contains. And both of these Sudoku requirements are both statements about this function. Namely, this first requirement, that each digit occurs in each row at least once, that's a statement that for each row, this associated function is onto. And then the second statement, that each digit occurs in each row at most once, that's the statement that this function is one-to-one. That is, I don't send this box and this box to the same number, for example, because that would be putting 2 2s in a row, for example. So, what does the Pigeonhole Principle Part 4 tell you about Sudoku? It tells you that these two rules are redundant. It would be perfectly sufficient to give only the first rule, or only the second rule, because the number of boxes in the row is 9, and the number of digits is 9, and so as soon as you know either of these two things, the other one doesn't need to be a rule of the Sudoku puzzle. It's an immediate consequence of the mathematics that underlie this. As a last note on the Pigeonhole Principle Part 4, I want to note that the Pigeonhole Principle Part 4 is the one piece of the Pigeonhole Principle that is exclusively true for finite sets, and there is no generalization, no interpretation of it that can possibly be true for infinite sets. That is, if I'm looking at a map between two infinite sets, even if they're the same size, it could very well be that the function is only one-to-one or only onto. Now, I want to show you an example of that, but we haven't really talked about sizes of infinite sets yet. But I think you will believe me if I claim that a set always has the same size as itself. And so if I look at my favorite infinite set, which is always going to be the positive integers, the thing I want you to believe for this example is that whatever thing I decide to call the size of the positive integers, it's the same as the thing I've decided to call the size of the positive integers. But even though these two sets have the same size, there's still a function from this set to itself that is 1-to-1, but not 1-to. And this is exactly the thing that the Pigeonhole Principle Part 4 says is impossible for finite sets. Namely, every function from a finite set to itself, as soon as it's 1-to-1, it's automatically onto. That's what the Pigeonhole Principle Part 4 says. And it's not just that direction of the implication that breaks. The other direction breaks too. That is to say, there also exists an onto function from the positive integers to the positive integers that's not 1-to-1. For finite sets of the same size, these two notions converge, 1-to-1 and onto. But for infinite sets, or sets of different sizes, the two notions diverge completely. They don't have anything to do with each other. This would be a fantastic time to pause the video and make sure you can come up with examples of both of these things. Come up with an example of a 1-to-1 function from the positive integers to the positive integers that's not onto, and come up with an onto function that's not 1-to-1. Okay, are you ready? I'm going to write down a function that's 1-to-1, but not onto, from the positive integers to the positive integers. Here we go. And that's it. I'm going to take each positive integer to that positive integer plus 1. So why is this 1-to-1? Well, the fact that this is 1-to-1 is, remember the claim that if f of x equals f of y, then that implies x equals y. But what does f of x equals f of y mean? Well, it means x plus 1 equals y plus 1. And so if x plus 1 equals y plus 1, that definitely implies x equals y. Just subtract 1 for both sides. Okay, so this function is definitely 1-to-1. Why is this function not onto? Well, this function is not onto because 1 can't possibly be in its image. Namely, there's no number that's a positive integer that I can add 1 to and get 1. Right? The smallest number in the image is 2, because 1 happens to go to 1 plus 1, which is 2. So it is not onto, but it is 1-to-1. Now, this particular function actually goes with a story that's often called Hilbert's Hotel. And what Hilbert's Hotel is you're supposed to imagine that Hilbert has a very large hotel with a room numbered 1, a room numbered 2, a room numbered 3, and so on. In fact, it's infinite. There's a room number for each positive integer. And in fact, we're supposed to imagine in this infinite hotel that the positive integers have decided to come stay at the hotel, and they're each staying in their own room number. So 1 is staying in room 1, 2 is staying in room 2, 3 is staying in room 3, and so on down the line. So in particular, one consequence of the fact that every number is staying in its own room means that every room is full. But then we're supposed to imagine, okay, well, every number is happy, but then suddenly 0 shows up. And 0 wants a room. And the people at the front desk, of course, say, oh, I'm sorry, 0, the hotel is full, there's nowhere for you to go. But then Hilbert, being the clever hotel owner that he is, and wanting the fee for the additional room, says, wait a minute, there actually is a way for 0 to stay in the hotel. All we have to do to get 0 to stay in the hotel is to move 1 to room 2, because that frees up an open room. But then 1 and 2 are the same room, and we don't want that. So then 2 has to move to the next room. So now 2 and 3 are in the same room. But we don't really want that. So then 3 has to move to the next room. But actually, if we keep doing that, so if 1 moves to room 2, 2 moves to room 3, 3 moves to room 4, and so on down the line, actually now this room is open, and 0 can stay there. And this is totally unlike how things would work if you owned an actual hotel. If you owned an actual hotel with, say, 300 rooms, and all 300 rooms are full, and someone shows up and wants a room, you cannot shuffle the guests around in some weird way so that now there's an open room. But somehow this infinity is fundamentally different than the finite numbers in the way it behaves with regard to this, and so you're able to sort of sneak this extra number in. And so that's exactly what's happening here with this function. So what's really being described here? What's really being described here is a function that goes from what to what. The function is really going from the number to the room number. So in terms of the hotel, what this function is really describing is a function from z plus to z plus that's taking a guest, because remember the guests are literally the numbers from 1 on forever, to their room number. And so in this first example, what we did was say it's possible to assign every guest, all the positive integers, to a room while still having a room be empty. So what we did there was to say that it's possible to assign all the guests to a different room and still leave a room empty. Okay. Every guest to a different room is saying one-to-one function, and then leave at least one room empty is saying that it's not onto. We did not use the whole codomain. If you did not get this example, you might figure out what this example is saying in terms of hotel rooms, and that might help you figure out an example of a way we can write down a function from the positive integers to the positive integers that's onto, but not one-to-one. So first of all, what does a function that is onto, but not one-to-one mean in terms of guests and rooms? So onto means every element of the codomain is used. So it means every room is occupied. But then what does not one-to-one mean? Well, it means not every pair of people end up being in different rooms, so it means at least 2 people share at least one room. And so I think it's not so hard to describe a way in which at least one room has 2 digits in it, but every room is still occupied. Namely, let's just say room 1 actually contains 1 and 2, and then room 2 contains 3, room 3 contains 4, and so on down the line forever. Every room is full, but this room has 2 people in it, not 1. Now, I can translate that back to an actual written down function. Namely, what did I do here? Well, where do I send 7? Well, 7 goes to room 6. Where do I send 4? 4 goes to room 3, and so on. And so what you'll figure out pretty quickly is that guest X goes to room X minus 1. Almost. But there's one exception. Because guest 1 can't go to room 0. There is no room 0. Don't be silly. And so, in fact, we need to write down that this is for X not equal to 1 specifically, and then for 1 specifically, we send 1 to room 1. And so to describe the function that we just described in the hotel, we would write this sort of piecewise function. I send every positive integer to that positive integer minus 1, except for 1, which I just have to send to 1. And so then 1 and 2 both go to the same place, so it is not 1-to-1, but certainly every room is used. I will leave for you to write out the complete proof that this is onto, but not 1-to-1. But if you have questions, feel free to ask about it during class. I will be happy to go over this proof in detail if you would like. I'm going to give one last note for today about bijections, which is then going to lead into our discussion in the next video. And that last note is that if you think about what a bijection means, again, we said it's 1 arrowhead for each dot, exactly 1 arrowhead. Then I can do the following trick. I can delete the arrowheads from this side of the arrow, and then just put an arrowhead on the other side of the arrow, And what's happened here is I've turned a bijection from A to B into a bijection from B to A. And the reason why this worked is that there was exactly one arrowhead at each of these points. If there had been more than one arrowhead, this wouldn't be a function anymore, because then I would have two arrows pointing from the same place. Or, if there were 0 arrows pointing from one of these things, well, now I'd have a function that wasn't defined on its entire domain. But exactly in the case that my function is a bijection, I can write down a function in the other direction that's also a bijection. And so at their heart, one way you can think of what a bijection really is it's a function that's reversible. That is, it's a function from A to B that I can turn into a function from B to A just by reversing the arrows. So in the next video, I'm going to make precise what it means for a function to be reversible. And we're going to talk about the reverse of a function, which is what ends up being called the inverse function. And then we're going to talk about how to use the notions of inverse functions to prove that functions are bijections in a way that's sometimes a little easier than the way we did in this video. And then we're going to talk about the inverses of the functions that we know and love, so e to the x and sine of x and x squared and all of these good things. But that's all for today. I'll see you next time.